Hi folks, Mr. Ackerman here. Thanks for watching. In this video, we're going to go over what I'm looking for you to do and hand in for the ball bearing bounce lab, which you can find in your course pack. You'll see it here. I encourage you to read through everything. Because you're not with me, there are parts of this that we actually aren't going to do together, so I'm going to steer you toward the things that we do need to do from where you are. The key is this diagram right here. It kind of explains everything. You're going to be rolling a ball down a launcher or a ramp. It's going to roll on a horizontal tabletop. It's going to have some velocity when it goes over the edge of the table. We're going to call that the instantaneous velocity, the initial velocity, and it's going to follow a parabolic path down to the ground. In the lab, the person who designed this lab, it wasn't me by the way, wanted his students to measure the speed on the tabletop and figure out, based on any measurement of distance and time, how fast the ball will be going when it gets right over here. In other words, not over here where you do the distance and time measurement and get an average velocity, but here. So there's already a little bit of a question mark in your head, like, are those going to be the same? More on that in a moment. Anyway, then he asked his students to measure the vertical displacement, delta dy, and based on that and their calculation of the launch velocity, figure out where the ball would hit. And then he was going to test them by putting a target down there, like maybe a cup, and see if the ball went into the cup. And if they did, then they get a cookie. Way to go. Well, we're not doing this part over here. We're going to concentrate on this part. And when you make your measurements, which will happen in a moment, I want you to think about uncertainties, which we've been studying. The way you're going to make the measurements is I have filmed 10 trials of the ball rolling across the tabletop, and you'll get to examine those in a moment. So let's jump in to a little bit more detail here. Like I said, when the ball rolls down, it's going to travel a certain distance, and you can use your stopwatch on your phone to measure the time. But remember, distances and times, they give you average speeds or velocities. So think about this. You're going to be getting the average over this interval here, okay? Right in here, you're going to get the average. But what they really want from you is to know when the ball gets here and goes over the edge, what is its initial velocity? And that's an instantaneous velocity that we need to know. If the ball moves at a constant velocity on this tabletop, then we just measure the average anywhere we want, and that's the same all the time, so we know the instantaneous. But think about this. There's going to be friction, so I think it's fair to say that the ball will be moving differently at the beginning of your interval than it will at the end of your interval. I think it's safe to say that it'll be a bit faster at the beginning, and then due to friction, it's going to slow down a bit. So let's say this will be slower. What are we going to do then? Well, there's an idea in physics which says when a thing slows down, if it slows down at a gradual or uniform rate, then the average, so this thing here, will be equal to the instantaneous somewhere in the middle. In fact, it's at the middle time of the interval, not the middle distance, but the middle time. But for simplicity, we're going to pretend that if we measure the average of a slightly slowing down ball, then the average velocity equals the instantaneous somewhere in the middle. Here's where the instantaneous equals the average. And that's kind of what the lab is telling you to do. The guy who wrote it is telling his students, once you know this point right over here, what I want you to do is move the entire apparatus so that that X, that point, corresponds with the edge of the table. And that way, when you roll the ball down the ramp, the average that you've measured is exactly how fast the ball will be going at that point. And if this point can just be shoved over so it's here, then we'll have a pretty good estimate of this number. And when you know the vertical fall, you can figure out where the ball will land. So, but like I said, we're not doing this part in here because you aren't here to test your predictions, unfortunately. All right? We're going to concentrate on this. In a moment, you're going to see the video and you're going to make measurements which help you figure out that average. And you're going to be thinking, hold on a minute, this is a measurement. There's distance and there's time. The distance is going to have an instrumental error. So will the time. At the same time, there's going to be a statistical error for both of these. What will they be? How much? How big? And what is your reason for choosing those? That's what I'm marking in this lab. Your thinking and your ability to communicate that thought. All right, so let's take a slightly closer look here. Here's two screenshots of one of the trials. The ball has already come down the ramp, and in the beginning here, it's located along this ruler. This is 0, 10, 20, 30, and so on. It looks like it's at about the 20 centimeter mark. This is at time 0. Now, a little while later, the ball has progressed along, and it is here, which is the 80 centimeter mark. Now, these are points that I chose. You can choose different ones if you want when you see the video. I'm just showing you an example. But this is going to have a different time. I got to use my stopwatch on my phone to figure out what that is. And if I do like 10 of these trials, I'll get a pretty good idea of the average from start to finish. So in a moment, you're going to construct a data table saying trial number and the time. And it's going to go 1, 2, 3, 4, 5. I think there's 10 of these things. So 1, 2, 3, and so on. And you'll have whatever you write in there. And then later on, you'll find the average. And that'll help you find VAV equals delta D over delta T. And you know how it was intended you would use that. You would use it to predict where the ball would land, but we're not doing that part, right? Okay, here's the thing though. As you watch this, just as a reminder, I want you to think for the delta D that you're about to see, whatever you choose that to be, it's your choice. Okay? You can get together in groups and figure it out, whatever you want. You can do it individually, it's fine. You choose. I want you to think of the delta D, what is the instrumental error, and what is the statistical error. Watch those trials over and over and see if you can decide. Tell me the number, the value. That's a quantity. So you're going to hear me use the word quantitative analysis. And I'd like to know a reason in words, a reason. Give me a qualitative analysis of what's going on here. A description of the challenges that were inherent in the measurement and how you dealt with them and how you analyzed how much they would impact the actual measurement. That goes into your uncertainty. Then do the same for the time. Give me your best guess for IE and SE as well. I'm going to be marking your thinking, your analysis skills, and I'm also going to be measuring your ability to communicate these to me in writing. Okay? We're now going to go to the video and watch the 10 trials, so get ready. All right, guys, so at this point, you've had a chance to time the 10 trials, and you should have a data table looking something like this. Time, or probably we'll start with trial number, and the time, and 1, 2, all the way up to 10, and you've got values in here. And what you're going to do is probably want to find the average time. That makes sense. There's nothing new about that. And of course, you're going to add up all of these and divide by 10. Now, you have a displacement that you chose, and that is constant. It's the same for every trial, so it does not need to go in your data table. You can just write that separately. But the interesting thing that I want to get to, as I said, is this. For the delta D, what was your IE and Y, and what was your SE and why? You need to be able to justify these. And if you want to speak with each other to come up with ideas, or if you want to do some research to find out how to handle that, by all means, go ahead. You know, the internet is your friend. You can use it to try to learn as much as you can about how to deal with observations. Same thing for time. When you calculate that time, you're going to have your SE and your IE. And I'm going to ask, what are they and why? Now, I'm going to want you to do a calculation. So let's pretend for a moment that you had something like this. Delta D over delta T, let's just pretend 75 centimeters plus or minus 1 centimeter. And let's say you had a time of, I don't know, actually I'm going to do 0.75 seconds plus or minus 0.075. Now, I'm not telling you why I chose these. That's up to you to figure out, and you got to justify it. That's where your mark's coming from. I just picked these as easy numbers that I could work with. So here we go. What is this going to be? Well, we're dividing here. So first of all, I know that this is going to give me 100 centimeters per second. That's easy enough. The plus or minus, if you remember from the instructional video, you have to convert these to a percent. Now, I purposely chose this one down here because I knew it would be 1%, but that was before that, when I chose the 1 centimeter out of 75, I didn't make a very good choice for a quick calculation. Okay, this comes out to 1.33%. Okay, so you remember from the instructional video on uncertainties, when you're dividing, you convert the percentages, the uncertainties to percent, and you add them. So this will be plus 2.3%. Now, luckily, that's going to make the next calculation easy. That's going to be 100 centimeters per second plus or minus 2.3 centimeters. So there you go. I've gone from absolute uncertainties, which is what we call it when you have the actual units, right? And then I've converted them into relative form, which is what we call it when you have the percentages, because we need to add those to get the total relative uncertainty. And then we convert back to absolute. And presumably this is the speed of the ball at the midpoint of the displacement that you chose. And if you were doing the lab live in class, you would now pick up the apparatus and move it so that the midpoint of your displacement was at the edge of the table. And then you would predict where the ball is going to land, you would roll it. I would go check whether that's actually where it lands, and if it did, you'd win a prize. We're not doing that part, so don't worry about it. What are we doing, and what do I want you to hand in? Let's take a look. There are a few things, and I'm just going to move myself over here so I'm not in the way. Okay, this rubric right here is in the course pack, and I'll move to it in a moment. I'm just working out of your lecture notes for now, but I want to point out that whatever you do, make sure you have made quantitative observations, especially for uncertainty, and qualitative ones. We've talked about this several times. It also says, get your observations signed before you leave class today. That obviously doesn't apply because you're probably not doing this live and in person. So what we're going to do now, I'm going to jump to Adobe Reader where I have the course pack open, and we're going to continue scrolling down through the ball bearing bounce lab until we get to that rubric. It's just a little bit nicer to look at it here, so we're going to view it right here. Okay, let's zoom in a little bit. First thing that you're being asked to hand in is what's called a sample calculation. Okay, now when you do a lab in science and there's many calculations, you often provide one sample, and then you say, now, I know I calculated this thing 10 times. I don't need to show you all 10 calculations. I'll show you how I did one of them, and then you can assume I did the other ones the same way. So we call that a sample calculation. So I would like to see a sample calculation that is complete and is detailed and is step by step only for the ball's initial velocity, not for other parts. If you show me the part with the ball going over the edge, that means you didn't follow instructions, because I've said repeatedly in this video it is not required. All I want is for the initial velocity. It's got to include uncertainties, units, and substitutions for all of your calculations. I also would like you to include your own fully labeled diagram showing the path of the ball from the top of the ramp until impact. So this is the one part I do want you to show from start to finish, is a diagram. I want you to get used to making diagrams and labeling them on computer, even though we didn't do the part where the ball goes over the edge. What else? Next up, error analysis. This is where I'd like a reasonable, meaning the numbers you're going to show me are not crazy, they're well thought out, detailed, so you explain everything, you don't leave things out for me to guess, qualitative, so a word description, and a quantitative or number description of the sources of error and the resulting uncertainties in your calculation. So in other words, justify what you put for IE and SE. Again, I've said this several times in the video, and I'm repeating it so that you'll know what I'm looking for, not because I'm trying to put you to sleep and make this video longer than it has to be. Note, you are not being asked for any of the projectile motion calculations. Do not include them. Word of warning, you might think you're impressing a teacher or a professor by giving more, but actually what you're saying when you include things that weren't asked for is you're saying, I didn't read the instructions, I didn't follow them, and now you're actually making it a little bit more difficult for the teacher to find what he or she is looking for. So I know you have the best of intentions, but please do not do that. Just put in what I've asked you for. Now, all parts of this report must be typed, made on computer, including the sample calculation. So you're going to need to use what's called an equation editor to type equations properly and professionally in Microsoft Word or Google Docs. And I'm going to show you how to do that in a moment. In the end, I'm going to mark your knowledge and understanding out of 5. It should take no more than 1 page in regular 12-point font to show me the following. All of the steps, substitutions, units, symbols, and uncertainties for your sample calculation, done correctly with the final answer in absolute uncertainty form, and a diagram showing the lab setup in thorough detail. Do all those things and get yourself hopefully a 5 out of 5 level 4. For thinking, I'm going to be looking that your data analysis, your error analysis, your uncertainties analysis was done in a reasonable way, identifying all the sources of error and their effects described in words qualitatively and estimated very accurately numerically, quantitatively. Again, maximum 1 page. Don't make more than it has to be. Try to keep it as efficiently communicated as you can. That's where your marks are coming from. All right, let me move myself back down here, and we're going to jump back to this. All right, so you're thinking, I've never made a lab report on computer. I don't know how to type equations. What's this guy expecting me to do? Well, I got your back, don't worry. A long time ago, I made a YouTube video called How to Create Lab Reports on Computer. The link is in the Google Classroom assignment for this lesson. It will show you how to type physics equations with the right symbols in Microsoft Word. And it also shows you how to create drawings using the sketching app I use called Sketchbook. You can look it up, it's free, okay? If you can't find that, use any other sketching app you want. Just make it look professional, not terrible handwriting, but proper diagrams with straight lines and nice looking fonts for anything that you've labeled. Now, some of you don't have Microsoft Word. So if you don't have Microsoft Word, you can use Google Docs because they have added an equation editor since this was created, since this video was created. Let's go take a look at how to do it. You can see how to do it in Word by watching this video. I'm not going to take up more of your time now, but for Google Docs, I don't have a video for that, so I'm going to show you here. You go like this. You've got all your typing, blah, blah, blah. This is what I think the SE and IE for displacement. Here's what I think. And then I'm going to do the SE and IE for time. These are what I think. Okay, that's part of it. But the other part is the sample calculation. Okay, so here's what you do. I looked this up. You can look it up. Do a Google search. How do I type equations in Google Docs? But just to show you at least once, insert, and you're going to go to equation. And you see these things up here? Check them out. All the Greek letters you might need. All of the mathematical operators you might need. Some more mathematical symbols. Now here is where you can do things that are kind of interesting, like make an equation, a over b, or a square root sign, or something like that. So watch. If you want to say v equals delta d over delta t, you go v, down here, equals, and then you go in here and you pick the thing you want to create, which is an equation. Now we need delta. I can write d here, and I can write t down there, but I want delta d, so I'm going to go in here to my Greek letters. I'm going to find delta. There, oh, no, there it is, delta d, and then I'm just using the arrows right now to move through here. There's delta d over delta t. And if I go equals, now I can start typing in the actual numbers. What did I use again? I think it was 75.0 centimeters, and now I need a plus or minus. Where the heck is plus or minus? Here it is. Whoop. Plus or minus. I think I used 1.0 centimeters. Now I can arrow back into here. There it is. What did I use for time? I think 0.75 seconds, and then a plus or minus 0.00, I think I used 75, something like that, whatever it was. And you're going to show me every single step nicely formatted like this. So not handwritten, not doing something like v equals d over t. That's amateur. We have a professional way to do it, and that's what I'd like you to do. All right? So to wrap up, you now know all about the lab and how it works. You know the part that I want you to hand in. You can read about it in this rubric here. You have this video to go back and look at if you need to. That's all for now. I'm looking forward to seeing your reports. If you have any questions, you know where to find me, and I hope to see you in class someday soon. All right, take care, guys. Bye for now.